All right, so announcements. So the lab this week is NetLogo. So first sort of full simulation. So we kind of started with Monte Carlo runs in Excel. Now we're doing NetLogo, so a special purpose simulation application, and then you'll be starting on Arena next week. So the many of the lab assignments for Arena will be based off of assignments that come out of the lab textbook. There, I've tried to put versions of the lab textbook that are available linked from Canvas. So if you're having trouble finding the lab textbook or you want a digital version, take a look there. But just in general, all starting with Lab 5 next week, you're going to need access to a textbook. And I say during lab, but of course, these labs are flipped. So, whenever you are doing the lab, you may need to follow along. So usually we'll say, well, we're going to start on this exercise. We're going to modify it in this particular way. So look out for that. Homework B1 solutions, again, they're available on Canvas. They've been graded. I just need to review the grades from the grader and then release them hopefully later today. And then, of course, there's ICAs. Looking forward, homework C2 is available. That's due next week. So not this upcoming Saturday, but I'm sorry, this is due. So today is third, right? Yeah. So it's due next Saturday. So lecture D2 will be Tuesday. So this is due the Saturday after that. You'll have to do a little book reading because it's sort of based on lectures E1 and E2, and E2 actually comes after the due date. I have to kind of squeeze things together because I want to make sure that you have time to practice and get a solution set for random variate generation, which is what we cover next week. And that is homework D2, which I'll hopefully probably release today, actually, but if worse comes to worse, Tuesday. So this is homework C2. Like I said, the stuff that you have to read ahead is pretty much plug and chug. I'll say for clarifications, if for some reason you've never seen this A mod B, this notation A mod B is just the remainder when you divide A by B. So 11 mod 2 would give you 1, or 11 mod 3 would give you 2. So if I divide 11 by 3, I get 2 remaining. So 3 times 3 is 9, plus the 2 gets me up to the 11. So that's just the remainder after division. In this homework, question 1, you have to calculate some random number generations. And so I want you to include the formula for each step. I'm only asking you to calculate, I think, 5 numbers. And so, show me your work, how you're calculating those. Actually write those out. So I know you could implement those in a spreadsheet and just give me a list of 5 numbers, but it's only 5 numbers. So I want to make sure that you can confirm that you know exactly how to apply this particular random number generator to generate those numbers. In question 2, if you summarize your results in a table, indicate the formula you use in table headers. And there are examples like that in the book. So make sure you're showing us what you're plugging in to make all this stuff work. Otherwise, like I said, homework D2, I haven't released it yet, but I'll release it either today or worst comes to worst on Tuesday. That's a random variate generation problem. So in homework C2, that's about generating random numbers and testing for the properties of random numbers. In homework D2, that's about generating random variates and confirming that you've generated the right variates from the right distribution. So that's will be released soon. And then the solution set you'll have before the midterm. There's a Canvas activity F. This is going to be a special Canvas activity. This is after E1 is due. F will show up. And F isn't available now because F actually samples from all of the previous ICAs. So it's meant to be a practice exercise that will randomly sample from the previous ICAs. And you can complete it multiple times and it'll take your highest grade. It's longer than previous ICAs because it's worth like 3.5 times a normal ICA because it's sampling from all of these previous ICAs. So it's not a full length ICA for each one of those, but even if you sample a couple of questions from each and then you add all that up over all the units we've covered, then it still ends up being longer than a normal ICA. So that's why it's so long, but you can take it as many times as you want and it'll keep the highest score. So it's meant to be a review, helped for a midterm review. And I make it due before lecture F. Lecture F will be the lecture right before stage one. So I think the way things are scheduled this semester, lecture F will be on a Thursday. And then in the week before fall break, stage one is a Tuesday, stage two is a Thursday. And for those making travel plans, remind this is Canvas-based exams, and you don't have to take them here. They can be taken remotely. But the idea here is that lecture F will be the Thursday before that week. And so I make this Canvas activity due before lecture F to try to get everyone going and reviewing that. So when you come to the review session, you potentially have, it's a higher probability of having questions about any of the past material that we can go over. Because for lecture F, all I do is I take questions, work problems, and then I also, in case there aren't any questions, I've got a slide deck of kind of what I think are the greatest hits from all the previous lectures. So just a couple of slides from every lecture, just as a reminder of what we covered in that, just to try to generate questions. So that's kind of the plan for the lecture right before that stage one, stage two week. So then as I was hinting at here, then the week before fall break, we've got this two-stage exam. So as a reminder, we've already talked about this, but I'll be here during that stage one and stage two. During this period, you're free to come here, but you're not required to. Stage one and stage two are both Canvas-based exams. So if you come here, you have to bring a computer to take it on. But stage one is a lockdown browser timed exam. So anytime that day, you can start it, and then it'll start the timer, and you have to finish it within that 90 minutes. And then you're done. Then you don't get your solutions. You don't get your scores right after stage one. Then stage two happens. That's a collaborative open book version. So in that one, it opens and it's not timed. So anytime that day, you can come back to it and update your answers. And in that one, you can talk to anyone currently enrolled in the class, and you can use your Canvas, you can use your notes, you can use any resource that I've provided. And it's the exact same exam as stage one. So then your total midterm score is 80% the score you get from stage one, plus 20% the score you get from stage two. And that will be your total midterm score. So that's what actually then goes into the grade book in that. So that's, and then stage one, like I said, is closed book. For stage one, I'll give you two-sided hand-produced sheets. Those can be typed, but they just can't have any screenshots in them. And then stage two, again, is open book, open notes, and it's collaboratives just so long as it's people in this class. So if you take stage two, not in the classroom, you're free to collaborate, on Discord, Slack, etc. But I'm trusting you to ensure that, and the only ones in the channel are going to be other students who are currently enrolled in the class. Any questions about that, the schedule moving forward? Okay. Then their standard reminder is that if you're interested in this competition, this can count towards your final project. Entries are due at the end of September, which is coming up. So any questions about that, admin stuff? All right, so let's then talk about probability. We have to talk about probability because it's a stochastic modeling course. What do we mean by stochastic modeling? So as a reminder, we are trying to simulate systems with realistic variation. So if you talk about people arriving to an airport, arriving to an emergency department, these sorts of things, then there's going to be spacing between those people, and it's probably not going to be regular. So we then have to say, and we are interested here rather than the average arrival rate, which, we use that as a parameter, but we're interested in what can happen when, even though you have an average arrival rate of 5 passengers per hour or something like that, occasionally you'll have some hours where you'll get a clump, you'll get a burst of traffic of 30 passengers, or you have some hours that have no passengers. And so in the ones that have a burst of traffic, then suddenly your performance metrics will go way down because of a lot of people wait in line. But then the other hours that you have hardly any traffic, then you're going to be wasting money in the resources. So you're going to paying people to do work that they're not going to be doing. And so how do we, what's the worst that can happen? So how do we cope with these variations? So we need real variation on our systems, but it's really hard to model real variation. So instead of modeling the real sources of the real variation, which are probably outside of our system and fairly arbitrary, we bring our system boundary in and we say, we're just going to pretend like this variation is being sourced by a random source, by quantum mechanics or something like that. And so we are using randomness to model the source of this variation, even if it's the actual variation theoretically has a deterministic source. So rather than trying to figure out the perfect model for based on the family size and where people live and all these things, the most likely distance between people who arrive at an airport, every time someone arrives, we can just roll the dice. And based on what comes off the top of the dice, we can say, oh, that's a 6. 6 corresponds to a long duration. Oh, it's a 2. 2 corresponds to a short duration, and so on. So we can set up these rules where as long as we can roll a dice and we can set up rules that map from all the faces of the dice to the die to these outcomes, then that mapping is now a tool for us to shape that to the world. And that's what we do in input modeling, is create these random inputs to our system that look like real world data, but we don't have to know all the details about the people behind the scenes. All we need to know is that, some statistical historical data about arrivals at the airport. We don't care who is generating the arrivals. We just know at that particular airport, there tends to get 10 arrivals per hour, and it happens to be Weibull distributed, or distributed is some distribution that we are aware of. So if you know the distribution type and you know the parameter or parameters of that distribution, then you can fill in the rest, and you don't need to know anything about the entities that are coming into the system. That's what we're doing. And that's stochastic modeling, is that stochastic, it comes from the Greek for guess or conjecture. So it is not a synonym for randomness. It is a modeling stance that even though the real system might not be random, it will be easier for us to build a model if we assume it's random. That's what it means to be a stochastic model. So input modeling is how we choose those models. Another way to view it is because we have, rather than saying like, oh, I'm introducing randomness that's not there, another philosophical way to view this is I don't know a lot about what generates the variation from my entities that are out there. I don't know about these passengers. And so I have to, because I don't know about them, that introduces uncertainty. And a stochastic modeling approach effectively models that uncertainty with randomness. So that's another way to view it, is that because I have less knowledge about what's actually going on in the real world, then I've introduced noise in my system. And so if I don't have noise in my simulated system, then I'm implying that I know the world perfectly. So the noise that I introduce is me admitting that I don't know information about the real world. And so I need variation to help account for the information that I don't have access to. So that's another stance on what stochastic modeling is. Either way, we need to know how to deal with random variables, and that's why we have this lecture today. And moving forward, that's why we'll be using so many probability-related concepts. Okay, so questions about that idea? What I mean by stochastic modeling? Using randomness even though the real world isn't random? Okay, so what are we in probability theory? So this is, it's somewhat review, but we're going to try to make things a little more formal, a little more rigorous, sort of step things up a bit from maybe some of the coverage you've seen before. But probability theory is a branch of mathematics called measure theory. Measure theory is a branch of mathematics that builds things that weigh stuff, basically. So measure theory is all about objects that have a finite mass, cutting them up into pieces and weighing them, and have weights that end up making sense relative to the weight of the whole object. That's what measure theory is all about. And probability theory is a subset of that, where instead of weighing physical objects, we're weighing events that have certain probabilities. So that's what we'll get into here. So that's kind of what I'm trying to show pictorially here, is that in measure theory, we have these things called measures, which are going to look like probability metrics in probability spaces. And so you have a whole object here. You can cut that object up. And if you measure the whole object, its weight will be the sum of the weight of the parts of the object. So it turns out that it's not trivial to build things that have this property, but this is the property you want if you want to build things that weigh stuff, or if you want to build things that have to do with frequencies of events. Because if things happen 100% of the time, then if you take a subset of them, you want them to happen less than 100% of the time, but you want to make sure that all of those things add up to no more than 100% of the time. So weight and probability go hand in hand together. All right, so what are these terms that I'm going to be talking about? Random variable is a term we talk about a lot. A random variable, unfortunately, is neither random nor a variable. A random variable is a mapping. A random variable maps from possible outcomes to a so-called measurable space. So we say that outcomes are mutually exclusive results of an experiment. So I'll give examples of outcomes here, but like in a die roll, each of the six-sided die, each one of the six faces, whichever one comes up, that's a mutually exclusive outcome. So there's six outcomes from rolling a six-sided die. So that's what I mean by outcomes. They're mutually exclusive. Only one of them can happen at a time. So in the measurable space, that's typically the real numbers. And so when I just look at this six-sided object and I roll it, it currently doesn't have any numerical properties. So I map it. I say, well, the thing with one dot on it, I'm going to map to a 1 on the real number line. The thing with two dots on it, I'm going to map to a 2, and so on. And that's what a random variable does. That mapping is that there are an outcome in physical world and you map it to a number on the real line. And once it's mapped to a number on the real line, then we can talk about the mathematical properties of the so-called image of those outcomes on the real line. And that's where we get probability density functions, probability mass functions, and so on. So a random variable is that mapping from outcomes in the real world to the real number line. So the number of coins landing heads up, that's a random variable as well. So in more advanced classes, you actually have to write out, this mapping. You have to make it clear that a random variable is a mapping from outcome space to measure space. For convenience, we often just drop that mapping in this class, and we'll just say, we'll call it a random variable X. But behind the scenes, X is this mapping from outcomes to the real numbers. We call the set of all outcomes the sample space, all mutually exclusive outcomes. And so the range of X is this image that I was talking about. So if you take all outcomes and you run them through the random variable and you see what subset of the real number line pops out, that's the range of a random variable. So if I have a six-sided die and I map them, the number of dots, if that's the mapping, then I have 1 through 6 are my outcomes here. 1 through 6 are my outcomes on the real line. So the range on the real line are just those 6 numbers. It's the discrete set of 1, 2, 3, 4, 5, and 6. That's what I mean by range. All right, so questions about this, just definitional. This will be maybe clear as we do more examples too. Okay, so building up from that, this gets a little confusing. There is a term in probability theory called an event. That's different than the event that we use in this class when we talk about discrete event systems. It's just something we have to deal with. It's just a collision of language. So an event in probability theory is a set of outcomes. So what I mean by that is I can say that like if I roll that die, an outcome is what face shows up the die. But an event is a set of those where you could say, the event is that the number of dots on the die is greater than 3. So 4, 5, and 6. That set of outcomes, 4, 5, and 6, is an event. That's what we actually measure the probability of. What's the probability of events? And so an event is a set of outcomes. So you can have events that only have one outcome in them. So a six-sided die shows 4 dots. Well, that can be a single outcome so that could be the outcome here, but I can create an event that only has that outcome in it. So then I can ask questions like, what is the probability that I'm only going to get a 4 on this six-sided die? But I can also say the six-sided die shows at least 4 dots. And so 4, 5, and 6. So joining those together, that becomes my event. So my events don't have to be mutually exclusive anymore. You can say, what's the probability that it's 4, 5, and 6, and it's even. So even is an event. That's 2, 4, and 6. 4, 5, and 6, that's another event. And when we talk about the probability of the two of those, we're talking about their intersection. And that generates a new event. So intersections of events generate new events, and we can take the probability of those. So outcomes are mutually exclusive. Only one can happen at a time. Events are not. They're sets of outcomes. So we then weigh those events with a probability measure. So we can say, what's the probability of an event? What's the probability that you get this set of outcomes? That's what the probability measure does. And because it is a weight, it has a conservation of mass property. So the weight of the sample space is 1. We just define that. That's the heaviest thing you can get. But then if you take any subset out of that, if you end up weighing that, it will be less than 1. And if you manage to create a set of events whose union is the sample space again, then the weight of that union will be equal to 1 again. So you can break things up and weigh them, and then those weights, when they add them back together, as long as you add them and you don't double count, will add up to the total weight of the sample space. So that's all I'm saying here. The weight of the whole sample space is 1, the weight of any event is non-negative, and all the weights add up to the constituent outcome weights. So that's another probability that is just inherited from measure theory. Questions about any of this? Okay. So we then are going to talk about discrete random variables. So we have continuous random variables and discrete random variables. Again, most of this should be review from 380 or 385, but a discrete random variable has a range which is finite or countably infinite. So countably infinite means it might have an infinite number of outcomes, but you can count them with the integers. So then that still makes them discrete. So this is different than discrete time or discrete event systems in DES. So a discrete random variable is a random variable that only takes on outcomes from a discrete set. And so that's a little different than what we talk about if we talk about discrete time, we might still describe state variables in our sims that can take on, that are continuous, but their time set is countably infinite. That's where the overlap is between these terms. So here we're talking about the value, saying that there's a discrete number of students that can be in this class because students are countable. But we can also say that there is a discrete set of cars. Now, whereas the discrete set of students in this class is finite, it has a maximum. The discrete set of cars that could drive by at any particular moment, well, it's theoretically that could be infinite. I mean, I guess we could probably calculate capacity constraints. So it's okay if it's infinite, as long as it's countable, it's discrete. So when we have a discrete range, so we have this countable set, we can assign a probability to each outcome, and we'll use this shorthand that the probability of an outcome is this, what we call this, this measure, probability measure, where the random variable is equal to that outcome. So we'll just use this shorthand where that's just saying the probability of that outcome. This is the kind of more formal way to write it. This is our shorthand. And so it inherits the rules from the previous slide. All the probabilities have to be non-negative, and they all have to sum up to 1. So this little shorthand here, this little p, we're going to call the probability mass function. We can only have a probability mass function of a discrete random variable. If it's a continuous random variable, which we'll talk about next, it's a density function. We have to figure out what the heck density is. But when it's a discrete random variable, it's a PMF. And if you collect all of the set of them, the graph of them together, an outcome with its probability, this collection we're going to call the probability distribution. So X is the number, as an example, X is the number of jobs arriving over a week. In principle, any non-negative count could arrive. It could be infinite. So that's a discrete random variable. So number of jobs arriving, no upper bound, but it is countable, so it is discrete. Any questions about discrete random variables? Yep. Mhm. Yeah, this means by definition. So, yeah, single equals means it is equal because it's like, like you could say like, 1 + 2 is equal to 3, and that just it is. But if I were to say G triangle equals 3, then it said, what the heck's G? Well, I just defined it. So I'm defining this shorthand. Okay. So you can think of the triangles like a delta, delta is like a D, so it's sort of like define. Other questions? Okay, so as an example here, number of spots face up on an unfair die. So here is our outcome space. Here's our range of the variables. So it can be any of these 6 on the real number, on the measurable space here. So outcome 1, we say we give probability 1/21, 2, 2/21, 3, 3/21, and so on, up to 6, 6/21. So we see that on this die, it's more likely to get a 6 than it is a 1. It's generally more likely to get higher numbers than lower numbers. So when we look at this probability mass function here, notice that there's all these denominators equaling 21. Where does the 21 come from? Why is that 21? Why isn't it 22 or 23 or 0 or 1 or 2? I guess not 0, but. Yep. It happens to be the sum of the x values, but why does it happens to be the sum of the numerators? That's even more important. Why are all of those normalized to the sum of the numerators? Why is it at 21? Yep. That's right. When you add them all up, they should all equal to 1. So we often see this. This is sometimes the physicists refer to this as a partition function. So the denominators of your probability distributions or of your probability mass functions and probability density functions, there's a related thing, but your denominators, your probability mass functions are normalizing factors that make everything add up to 1. So because the numerators all add up to 21, then when you add them all up together, is the denominators are 21, then the probability of all the outcomes are equal to 1. There are only 6 possible things that can happen in this random variable, so it better be the case that the probability of all of the possible things that can happen adds up to 1. So the random variable should be that it accounts for everything that could possibly happen. And so there's nothing left out. So if you add up everything that can possibly happen, something should have happened. So the sample space is itself an event whose probability is 1. It's a 100% chance that something's going to happen. And so the individual outcomes should make sure they add up to 1. So because of that, sometimes it's actually when you're talking to a stakeholder, you often don't want to ask them what the probability mass function is. You have to know how to talk to a stakeholder. And you're often more interested in like, how much more likely is it that X happens over Y? And if a stakeholder says, well, it's twice as likely that this will happen over this, it's 3 times as likely that this will happen over this, then you effectively can assemble these numerators, and then you worry about the normalization later. So don't ask stakeholders questions like, can you give me the absolute probability? Like, is it a 20% chance? Is it a 60% chance? They might not have that data, or they just aren't used to talking that way. So they might specify things in terms of relative quantities or whatever, and then you then apply the normalization factor later. Likewise, when you're presenting data to stakeholders, then oftentimes drop these denominators, figure out a new way to present these data, because the 21 is not interesting, it's a technicality. So saying to someone that this is a unfair die, that where the probability of rolling a 6 is 6 times as likely as rolling a 1, that's more meaningful than giving them this list. But if we want to simulate this die in a computer, we need this list. So you have 2 different audiences. The computer is one audience, the stakeholders are another, and the denominator is the bridge between the 2. Okay, questions about that? It's clear where 21 comes from. We just have to add up to 1. All of them are greater than 0. That's also the case. And if we wanted to plot it, this is how we plot a probability mass function. So we put all the outcomes on the x-axis with the probabilities on the y-axis. And notice I do not connect the dots. Each one of these little pins here, these kind of little, they just look like little pins, like pinheads and sticking in here. Each one of these we call a delta measure. So it just exists at that point. So in previous classes, you might have plotted probability mass functions by connecting these dots. You do not do that here. So in this class, and hopefully all classes moving forward, if you're plotting a probability mass function, there is no outcome between 1 and 2. So you don't connect the dots. There is no outcome between 2 and 3. So you have this comb-like structure that is up there, and that communicates that it is a discrete random variable. So that's why we're going to show these like this. They'll always look like this with these so-called delta measures. Questions about that visualization? Pretty clear. And also fine if you're just plotting dots. You don't have to draw the line connecting it down to the axis, but that's just for style, you could do that. Okay, questions, discrete random variables before we get to the more exotic? All right, so then continuous random variables. So that's the other side of it, the more general case. So a continuous random variable, this is a variable whose range is an interval or collection of intervals. So it's uncountable. There's no way to count the number of real numbers between 0 and 0.5. It's just uncountable. And so if that is your outcome, the number of between 0 and 0.5, if that's the range of your random variable, then it's a continuous random variable. And so we write the probability here in terms of this integral that we're going to talk about with this thing inside called a probability density function. So as we'll talk about, density is not the same as probability, just like density of a table is not the same as weight. So, and that is going to be the key thing. So the visualization you should keep in mind is this guy down here. This is the probability density function of a probability distribution, in this case, an exponential. So this density function sort of tells you how dense the material. It's densest on the left. It's less dense on the right. So it kind of will be heavier on the left than it is on the right. And when you say, what's the probability of an outcome between, or of the event of all outcomes between A and B, what you're effectively doing is saying, what's the weight of this slice? So if you cut this thing here and you cut this thing here and you then weighed the block that resulted, that's the probability. So that's what we're setting up here. So this density function does have properties that make it look probability-like. It's always non-negative. And it's only equal to 0 if the value is not in the range. The integral under the density is equal to 1. So that looks kind of like probability. But there is a key difference, and that is that densities can be greater than 1. The sun is a very, very dense object. It's extremely dense. That's what gives it. Gravity is pulling it together. The pressure in the sun, due to that density, due to that gravity, is what ignites it, turns it into this nuclear fireball, and so on. Extremely dense stuff. And so the density of the sun is very, very high. But if you had a sufficiently small amount of sun in a little teacup or something, it would potentially be something that has very little weight. In fact, if you had an infinitesimal slice of the sun, it would be 0 weight, despite it having enormous density. So density is not probability. And it gets confusing usually for students at this point. I think in part because the mathematicians, they just don't think in terms of units. And as engineers, we're taught to think about units. If we had units, it'd be pretty clear. Like if there was a unit of probability, let's call it a prob, then density would be like prob per meter. So it's the, if I was just saying like, or our prob per, let's say I was talking about the count of people arriving at an airport. And I could say prob per person. That would be the density. It would be like, as I add another person to my event set, how much does the probability go up? That's what density is. That's like the density of a table. Physicists like units, and so they don't have this problem about density versus weight because they know the table is so many pounds, and they know that there's a linear density, which is like pounds per unit length, pounds per meter or something like that. So that'd be every meter of this table, they know how many pounds are added. That's what probability density is. For every unit of X, it's how much probability is added. So density can be greater than 1, just so long as the area underneath the density is equal to 1. So that is something that's often very confusing, but it's just this idea that density has different units, so it doesn't have to be less than 1. And likewise, a point of non-zero density has no mass. So if I took an infinitesimal slice of this table, regardless of how heavy this table is, regardless of how dense this dense tabletop is, and it is dense, the infinitesimal slice would be 0 weight. So that's what we mean here when we say that even if our probability density function is near infinity, it's really high at that point, if you are only integrating across a single point, if you're saying what is the probability at a point of the probability density, it will be 0. So likewise, what we're saying is if you throw a dart at a dartboard, the probability of hitting any point on the dartboard is 0. The probability of hitting the bullseye is finite and non-zero. The probability of hitting the whole dartboard is finite and non-zero. So probabilities of regions are non-zero, but the probability of any point is 0. You cannot predict it with any, you can hit any particular point. There's no predictability in hitting points, but there is predictability in hitting regions. Questions about that? Density versus probability? Yep. Right here? Oh, up here. Oh yeah, so all this is saying is that if X is not in the range of X, then we force it to 0. So the what we're saying is the real number line is infinite, but the number of outcomes you're considering might not span the whole real line after the mapping. So anything else on the real line, we want to be able to integrate. All this is really saying is we want to be able to integrate from negative infinity to infinity, even if the range isn't negative infinity to infinity. Any other questions about that? Okay, so that was our picture from before. So we can see now here that this is a probability density function for an exponential random variable. So if I were to take the probability at a particular point, so what is the probability of x0 of a particular outcome, then it's 0. So this distribution often describes the inter-arrival times between people arriving to things, independent events, when people arrive to doors or whatever. And I could say, what's the probability of there being exactly 3.67 seconds between one person and another? That is always 0, regardless of what number I pick. Probability of any particular number is 0. But the probability of someone arriving between 3 seconds and 4 seconds in that range, that is non-zero. And so that's what we're saying here. Probability of any slice is 0, regardless of the density. The probability of any chunk is non-zero. And it is the area under the density function. Is that clear? So we mean by continuous random variables. They're a little weirder. That's why we have to use the integral for them. Okay. So mentally, like I said before, model continuous random variables as blocks, like a chunk of wood, and then shave into the top of the chunk of wood the probability density function. Another way to view it is a table like this, but enhance this part of the table with more weight and take away weight from this part of the table. That's a little harder to visualize. That's why I usually say just a chunk of wood that you shave the density function into. And then once you see that, a lot of properties of that density function become much more intuitive. As we'll talk about here in a second, the mean, the average value of that probability, of that random variable will pop out of the page, because you can imagine, where does this block balance So the balance point, if you were to sit this on a point and try to get it to perfectly balance, that's the mean. So think of this, try to, any intuition you have about weight in the real world, you can translate it directly to probability spaces. And it's just a chunk of wood. And so what is the weight of an infinitesimal slice of wood? 0. What is the weight of this chunk? Well, you can imagine how much it might be versus the weight of the whole block. Okay. So example, a lifetime of a device that inspects cracks in an aircraft wing. So we have a simulation of a process where you're inspecting aircraft wings going through, and there's a device which inspects it for cracks. And then if it finds cracks, it has to send the aircraft wing back through to get fixed. But that device will itself sometimes break. And when it breaks, it shuts down the whole line while we wait for it to get fixed. And so we need an input model for how long until it breaks. So our input model in this case is going to be an exponential random variable with a particular mean. We haven't talked about what a mean is yet, but we're about to. So the density function looks like this. This is a probability density function for an exponential random variable with a mean of 2 years for its failure time. And so it looks like this. And so somebody might ask, what's the probability of it failing between years 3 and 4? And all you do is you integrate under the curve between years 3 and 4. And that tells you, if I actually went and did the math, then that would tell me that, it's, I don't know, 20% or something like that. So that, allows you to do that analysis. You can't say what's the probability of it failing at exactly a particular time, because that will always be 0. But you can ask what's the probability that it fails in the first year, in the second year, and so on. Any questions about that? Our continuous random variable? Okay. So yeah, mean. Let's talk about the mean. We're going to get to that in just a moment. That's a pun, which I'm sure you all will find very funny in several slides. But before we get to the humor, then for a random variable x, we have to define not just the probability density function and the probability mass function, but the cumulative distribution function. And the nice thing, there's so many nice things about the CDF. The CDF is what you really, you mature into the CDF because it's so much better than the PMF and the PDF. And one of the wonderful things about a CDF is that it's exactly the same regardless of whatever probability, whether you're using a continuous or discrete random variable. For all random variables, the CDF is the same interpretation. And so a CDF is this capital F is the symbol we use for it, so defined as. So this capital F X is just the probability of that your random variable is less than or equal to this argument X. And it doesn't seem like much, but it is taking the probability from negative infinity all the way up to X. That is your CDF. So for a discrete random variable, you just sum up all of the outcomes less than this X inside the argument of the CDF. You sum up the probabilities of them. For the continuous random variable, you take the integral of the density function from negative infinity all the way up to this argument. And so behind the scenes, that's the difference between the discrete and the continuous. But once you have the CDF, once somebody gives you the CDF, then at that point, it looks the same. It can be handled the same, whether it's discrete or continuous. So you don't care how it was generated. It works the same way. So it's a very flexible quantity. And it has these really nice properties. So one of the things is F, the CDF, is a non-decreasing function. So if A is less than B, then F of A, it'll be less than or equal to F of B. So it's always not necessarily rising, but it's never falling. That's one nice property of it. It always ends at 1. So if you take the limit to infinity, it always goes to 1. It always starts at 0. So the limit on the other side is always 0. So it goes from 0 up to 1. It varies often S-shaped. And then this is a really nice feature. And we've already sort of seen this in your lab 3 with the Monte Carlo analysis when you're generating those random variables, or random numbers, is that the probability of being between A and B for any random variable is just the CDF at B minus the CDF at A. So I might, on an exam, show you a probability density function, and a CDF. And then in a problem for the exam, you might have to calculate the probability that outcomes are between two numbers. And your gut might initially tell you that, oh, I should do the integral. I should integrate the density function. But you don't have to do that if I gave you the CDF, because I've already done it for you. You just plug it into the CDF, and then you just do some simple arithmetic. So that's a really nice feature of the CDF. All right, questions about a CDF? What I mean by cumulative density or cumulative distribution, the probability from negative infinity to this point. Okay. So this is what CDFs look like. This is a CDF for a discrete random variable. It looks like stair steps. So I plotted it here with the open circles and the closed circles and these straight lines. So you can see there's these kind of broken steps here. But what's nice about it is it's defined for all of the, for the whole real line. So it's 0 up to this point, and then it jumps up and it keeps jumping up, and then it's 1 from this point on to positive infinity. So even though I do have these breaks, there's a no point is it undefined, and it's always rising, and that's our CDF. And so discrete random variables will have stair-step looking CDFs. And a nice thing about this, and this basically goes back to lab 3, is if I invert this function so that I make the y-axis the input and the x-axis the output, I can generate random variables from random numbers. And that's what you did in lab 3. So by inverting this, if I generate a random number between 0 and 1, I can then plug it into the y-axis, see where it hits the CDF, and whatever outcome that maps to, that's the outcome that I call my outcome. And the beauty about this is this will ensure that the probability of these outcomes matches the desired probabilities. And that's the so-called inverse transform sampling, which we'll talk about a little bit more in lecture E2. And you've already sort of started to do that. You sampled that, so to speak, in lab 3. Same story with a continuous random variable. We have, this is our exponential distribution. Its PDF looks almost like the mirror of this. So its CDF rises and it has an asymptote at 1. It's 0 for every point down here. And so it's just the integral, again, to this, so this point, the integral of the PDF to this point is here. The integral of the PDF to this point is here. So that's where we get the rising. And it has the inverse transform feature as well. So you want to generate exponential outcomes. Well, Excel does not have an already pre-built exponential random variate function. So you just can't generate exponentials from Excel based on anything that Microsoft has given you. But you can generate a random number between 0 and 1. And if you invert this CDF so that the input is on the left here and the output is on the bottom, then if Excel generates a random number between 0 and 1, you plug that into the inverse CDF, and these outcomes that you get out from that mapping will be exponentially distributed. So that's what's going on behind the scenes. That's, again, inverse transform sampling, which is something that we'll go into more in lecture E2. All right, questions about the CDF or about any of that, the inverse stuff? Pretty clear. There's just a sample of things that we can do with CDFs. Okay, so we can wrap up here and let's talk about moments. So the first moment that we really care about is the mean. That's the expected value of a random variable. And this is the center of mass of a probability distribution. And so it is the balance point of the probability distribution if you turn probability into actual mass. And so when you do moments in a statics class, so it's like from statics to statistics, then you do that for a discrete random variable, you can treat X as like if this was objects distributed along the table here, if I wanted to calculate the first moment of where that objects were, so this thing sitting here and so on, what I would do is I'd take the weight of every object in the distance that was away from the edge. And distance times weight plus distance times weight plus distance times weight, all of those things together would give me the so-called moment first moment of that weight distribution. And that is the center of mass of this distribution of objects. And so if there are kids on a teeter-totter, then if I place these objects, these different weights on that teeter-totter, that first moment calculation tells me where I put the fulcrum to balance out so that regardless of the kids' weights, then it stays horizontal. And that's exactly what this is here. And it's the same thing for the continuous side. If I don't have discrete weights, but if I have a tabletop that is a little denser on this side and less dense here and more dense over here, and it's smoothly varying, then if I take the integral, not of the density, but of the product of the density and the distance from the edge, then this new integral, that ends up giving me the center of mass of this tabletop. And that also gives me the center of mass of the probability distribution. And so that's what a mean is it's a center of mass. We call it an expected value. We also call it a first moment. Visualize it like this. So here's an exponential random variable. Here is the mean of this particular exponential random variable. If you shaved this into a block of wood that was uniform density before you shaved it, then this would be exactly where you put a fulcrum to balance this block of wood so that it doesn't tip on either side. So if you look at a probability density function, you can use your intuition about where you might put that balance point, and that can give you an estimate of where you would expect the mean to be. So it's not an arbitrary value. It is this, it balances out the effect of outliers in your data with common values. That's the idea of the mean. And that's the reason why the means are so sensitive to outliers, because they're trying to balance those two things out. Any questions about the mean? I know it seems like a simple thing. Okay. We do care about other moments in this class as well. So if I refer to the second, third, fourth moment, then it's this generic expression for discrete and for continuous random variables. So discrete up here, continuous down here. It's the same as the mean, but now that distance ends up getting raised to whatever the number that I said was. So the second moment is going to use n equals 2 in both of these expressions. The third moment, n equals 3. And each one of those moments extracts a piece of information from a probability distribution, similar to the balance point for the first moment. And an example of that is variance. So variance is a measure of spread. And variance specifically is a measure of spread around the mean. So the second moment is a measure of spread generically. So we define these things called central moments. And so I don't know if I mentioned here. So the idea here is that I can create a new random variable where I subtract the mean of the random variable away. And then I ask, what's the second moment of that resulting random variable? That's what we refer to as the second central moment. It's a central moment because I've subtracted the mean off. And it is the second moment because I'm taking the expectation with that little squared up there, which is just like the formula that I had over here. So that's the expectation with the little square there. So the second central moment is, it has a special name, and that's the variance. And it's the spread of a random variable after you have removed the mean. So when you've centered the random variable around its mean, what is its spread? That is where we get variance. And it's just the second moment. And the nice thing about it is that if I know the second moment of a random variable and I know the mean of a random variable, then I can very quickly calculate the variance with this handy little formula here. And so if very often you'll get random variables and it's easier to calculate, or you've already been provided all of their moments. And so if you already have their moments, then you can use formulas like these to calculate other properties of interest to you, like the variance. So you can go through and do the integral that requires calculating this, but this, if this has already been done for you, then you can just do the simple arithmetic and then you get the variance out. Standard deviation is just the square root of the variance, and these are the terms, or these are the symbols we use. We use a lowercase sigma for standard deviation and sigma squared for variance, as I'm sure many of you are aware at this point. Questions about the second central moment? variance or moments in general? Okay. So where we're going to go from here. So we've now generally talked about random variables, probability density functions, cumulative distribution functions. And so we now need to sort of talk about how to use them in things like queuing networks. We need to also then specifically talk about in input models, what are the most common random variables that we're going to use. So in this class, you're going to build a vocabulary of like, oh, for an arrival process, it's probably one of these random variables. For an additive process with fatigue, it's probably one of these random variables. For a type of count, it's probably one of these random variables. So there's going to be a set of 12 or so distributions that will end up becoming modeling tools like Legos that you end up putting together. And you say, for this part of the system, I'll use these input models. For this part of the system, I use these input models, and so on. So we have to learn, why do we have all these different distributions? Well, some have certain properties that make them more likely to model one thing. Others have other properties that make them more likely to model another thing. So that's what we have to build up awareness of. And then also for discrete random variables. And so not just these continuous things like arrival times, but also counts and other things that tend to show up as discrete distributions. So that's all we've got for this time. Any questions before I give you the clicker? Okay. So the clicker question, as I bring it up, will be, what is another name for the second central moment? So just give me a second to get that clicker back up. It was just here. Oh, I know exactly where it went. All right, I'm starting the short answer now. Okay, so the question was, what is another name for the second central moment? So that's a special moment that we give a special name to. So what is another name, a one-word name for the second central moment? Have a nice weekend.